So this example is very similar to the last one. We have the same object with an emissivity of 0.8, a surface area of 37.5 centimeters squared, but this time the temperature is 215 degrees Celsius. And we're once again being asked to find the total radiated energy output using the Stefan-Boltzmann law, of course, since we're given the Stefan-Boltzmann constant. And so if I look at the calculation I did in the last example, the only change I really need to make is this temperature here. So maybe what I can do is just copy what I already have right here. Just have to hang on. Let me just copy this part. Hopefully it will manage to do this for me. Okay, so we're doing that part. And then the modification will be is we'll want to use the new temperature. So it was 15 degrees Celsius in the last example. It's now 215 degrees Celsius. So add 200 to what we had before should work out. You can confirm that if you take 215 plus 273.15, that should be 488. Almost a whoops there on that 8.15 Kelvin to the fourth power. So this is the new calculated power that we get. And when I put that into my calculator, it gives the result of 9.66, and that should be in watts. I rounded that off. It was actually 9.65867356 if you want to compare with exact numbers. It's interesting though, because when you look at this in Kelvin, this is not even a doubling in temperature, and yet look at how much of an increase that was in terms of total radiated power. This example is meant to demonstrate what the ramification is of power scaling as the absolute temperature raised to the fourth power. Because it's raised to the fourth power, that's what explains that dramatic increase.